There was a stretch in Earth's history when ice held the planet in a grip that lasted longer than complex multicellular organisms have even existed on this planet. 300 million years of solid ice. And the culprit behind this catastrophe wasn't asteroids, wasn't volcanoes. It was the tiniest living things on the planet, which accidentally poisoned the air with a gas that, for most of the life alive at the time, was a lethal toxin. How did life nearly wipe itself out with its own breath? And how did a planet locked in ice for 300 million years eventually thaw back out? To understand that, we first need to see what the world looked like before everything started falling apart. Picture Earth around 3 billion years ago. This isn't a planet you'd recognize right away. Continents in the modern sense barely existed, just scattered. Small volcanic island arcs, gradually, over hundreds of millions of years, fusing together into the first tiny protocontinents. The sky would have looked strange too. With no ozone layer, solar ultraviolet radiation hit the surface far more intensely than it does today. And the surface itself most likely had a dull, brownish-green tint. Nothing like the familiar blue of modern Earth seen from space. But the biggest difference wasn't in the landscape. It was in the air itself. The sun back then was roughly 20 to 25% dimmer than it is today. A young star that hadn't yet reached the brightness it would eventually grow into over billions of years of nuclear fusion. By ordinary logic, that should have meant a frozen, ice-locked planet. Less heat from the sun should have meant a lower average surface temperature, possibly even a fully frozen global ocean. But Earth back then wasn't frozen. Quite the opposite. It stayed warm enough to support liquid oceans and active life within them, including, by some estimates, a nearly global ocean with no major continental ice sheets at all. And the reason behind this paradox, known to scientists as the faint young sun paradox, is hiding in the planet's atmosphere itself. The Archean atmosphere had essentially no free oxygen at all. Instead, it was loaded with other gases, ones far better at trapping heat, carbon dioxide, and, especially important for our story, methane. Methane is a far more powerful greenhouse gas than carbon dioxide, capable of trapping heat dozens of times more effectively per molecule. And a significant share of that methane on early Earth had a biological origin. Microorganisms called methanogenic archaea, some of the oldest forms of life on the planet, produced this gas as a byproduct of their metabolism, breaking down organic matter in oxygen-free environments on lake and ocean floors and deep within layers of sediment. Studies of the isotopic composition of ancient rocks, notably finds from the Canadian Shield, confirmed that this microbial methane really did build up in significant quantities as far back as the Neo-Archean, long before the oxygen catastrophe, serving as one of the main components of the thermal shield that kept the planet from freezing over. Together, these two gases, methane and carbon dioxide, built a powerful greenhouse blanket that made up for the weaker sunlight and kept the planet warm enough for liquid water to exist. This fragile but remarkably stable balance held for hundreds of millions, if not billions, of years. And it was exactly this balance that the most unremarkable residents of the ancient ocean were about to destroy. Somewhere between 3, 5, and 2, 7 billion years ago, a group of microorganisms appeared in the oceans of Archean Earth that would go on to rewrite the history of the entire planet, cyanobacteria. These single-celled organisms learned to do something that, most likely, nothing before them had ever done at this scale. Use sunlight to split water molecules apart, releasing energy for their own metabolism. The byproduct of this process, oxygenic photosynthesis, was a gas that, up to that point, essentially didn't exist in free form anywhere on the planet's surface, molecular oxygen. Traces of this ancient life are still visible with your own eyes today. Cyanobacteria lived in colonies, building layered mineral structures known as stromatolites, dome-shaped or column-shaped mounds that formed year after year, layer by layer, in the warm, shallow lagoons of the Archean Ocean. Fossilized stromatolites, found today in Australia and other parts of the world, still look almost exactly like the living colonies that survive today in a handful of isolated salty bays around the planet, living relics of a world more than 3 billion years old. At first, this oxygen wasn't a problem for the rest of the planet at all. The oceans at the time were saturated with dissolved ferrous iron, washed out of the Earth's crust over billions of years, and the freshly produced oxygen reacted with it instantly, forming iron oxides that settled to the bottom and built up what geologists today call banded iron formations. These rocks, thick layers of stone with a distinctive alternation of dark, iron-rich bands and lighter, silica-rich ones, can still be seen today in many corners of the world, in the Hamersley Range in Western Australia, around Lake Superior in Canada and the US, in South Africa. These ancient deposits today make up the vast majority of all the iron ore humanity mines to make steel. Quite literally, the foundation of modern industry, laid down by microscopic bacteria that lived billions of years ago. Stop and sit with that for a second and look around you. The steel beams holding up buildings around you, the car in your driveway, the knife in your kitchen drawer. Nearly every piece of iron and steel that's ever been made traces back to this. Microscopic bacteria, breathing, in the most literal sense, oxygen that rusted dissolved iron in an ocean 2 billion years ago, one layer at a time. They weren't building anything. They weren't planning for you at all. The foundation of modern industry was laid down long before a single multicellular organism ever existed on this planet. Essentially, for the first several 100 million years of their existence, cyanobacteria were literally rusting the ocean, not poisoning the air. The oxygen they produced was getting absorbed by chemical reactions faster than it could ever build up in free form. This was a kind of buffer, one that temporarily shielded the atmosphere from the consequences of this new, revolutionary form of life. But that buffer had a limited supply. Researchers studying the isotopic signatures of Archean rocks have found evidence that free oxygen may have appeared in a few localized oases long before the global catastrophe, possibly as far back as 7 billion years ago. Small, isolated patches of surface ocean or coastal cyanobacterial mats where oxygen temporarily built up in amounts detectable by modern geochemical analysis methods, notably through characteristic mass-independent fractionation of sulfur isotopes in sedimentary rocks from that era. These oases were a warning, the first tiny cracks in the planet's ancient, stable balance. But as long as the iron in the oceans was still plentiful, the global atmosphere as a whole stayed essentially free of oxygen, and the rest of the biosphere at the time, mostly anaerobic microorganisms for which oxygen was genuinely toxic, kept on existing, almost entirely unaware of the catastrophe closing in. But the supply of dissolved iron wasn't infinite, and somewhere between 2 billion years ago, that supply, built up and drawn down over billions of years of geochemical cycles, finally ran out. And once the iron buffer was gone, the oxygen cyanobacteria kept producing, without ever pausing, had nowhere left to go. It started building up directly in the air, the same air that essentially the entire biosphere of the time was breathing, or rather, not breathing, because it hadn't learned how yet. This was the moment when the quiet, slow, almost invisible work of microscopic organisms, carried out over hundreds of millions of years, suddenly hit its breaking point. And what happens next is something scientists today call one of the greatest ecological catastrophes in the entire history of life on Earth. We left the planet at a breaking point. The iron buffer that had spent tens of millions of years soaking up every molecule of oxygen produced by cyanobacteria had finally run dry. And now oxygen, for the first time in Earth's entire history, started building up directly in the air. Geologists date the start of this transition to somewhere between 3 billion years ago. Scientists named this event the Great Oxidation Event, or the Great Oxygenation Event. The moment free oxygen levels in the atmosphere climbed, by various estimates, to roughly 10% of today's level, a jump that, by geological standards, happened almost instantaneously. To a modern person, 10% of today's oxygen concentration sounds like nothing much. But for the biosphere of the time, which had spent billions of years evolving exclusively in an oxygen-free world, this was a catastrophe on a cosmic scale. The overwhelming majority of microorganisms back then were obligate anaerobes, forms of life for which oxygen acted as a direct cellular poison, breaking down proteins, damaging DNA, disrupting the very chemistry of metabolism inside the cell. This gas suddenly appearing in free, unbound form meant exactly one thing: mass extinction. Scientists today often call this the first truly mass extinction in the entire history of life on Earth, far older than any of the 5 classic mass extinctions of the Phanerozoic usually mentioned in popular science. The vast majority of anaerobic species at the time either went extinct completely or were forced to retreat into isolated, oxygen-free refuges, deep seafloor sediment, oxygen-free mud, hydrothermal vents, anywhere oxygen still couldn't reach. But the most destructive, longest-lasting effect of this event didn't touch living organisms directly. It touched the planet's climate itself. Remember that fragile methane and carbon dioxide greenhouse shield that had spent tens of millions of years compensating for the young sun's weaker light? Methane, the very same gas that had been keeping the planet warm despite the dimmer sunlight, turned out to be extremely chemically vulnerable to oxygen. The reaction between oxygen and methane happens fairly easily, oxidizing methane into carbon dioxide and water vapor. And carbon dioxide, while still a greenhouse gas, is significantly weaker than methane by a factor of dozens, molecule for molecule. So the moment oxygen started building up in free form, it immediately started actively eating atmospheric methane, converting a powerful greenhouse gas into a much weaker one. This was a double blow. The young biosphere was losing its main thermal shield at the exact same moment the sun was still shining significantly dimmer than it does today. Researchers traced this chain of causes directly. The sharp rise in oxygen led to a sharp drop in methane levels, and that drop in methane meant losing most of the warming effect that had, until then, been compensating for the young sun's weakness. The planet started cooling. And, as with any climate system like this, a mechanism kicked in capable of turning moderate cooling into a runaway catastrophe: the albedo feedback loop. As temperature drops, ice and snow start spreading outward from the poles toward the equator. And snow and ice reflect far more sunlight back into space than dark water or bare rock does. More reflected light means less absorbed heat. Less heat means an even lower temperature. And a lower temperature means even more ice. Once triggered, this feedback loop is capable of reinforcing itself with no outside help at all, right up until it hits a certain critical threshold, past which it's essentially impossible to stop through any natural process. There's one more factor that, according to some research, may have made this crisis even worse. Right around this same period, geologists have detected a marked lull in volcanic activity on the planet, a magmatic shutdown between roughly 245 and 2 billion years ago. And volcanoes, despite their destructive reputation, actually play a key role in stabilizing climate over the long term, regularly replenishing the atmosphere with carbon dioxide. Fewer volcanoes meant less replenishment of the very same greenhouse gas that had just lost its most powerful partner, methane. The geological record, preserved in thick layers of sedimentary rock around Lake Huron in the Canadian province of Ontario, which is where this entire period gets its name, captured not one, but at least 3 separate waves of glaciation that rolled across the planet in sequence, somewhere between roughly 245 and around 2 billion years ago. This wasn't one single, continuous freeze, but more of a repeating series of crises. The planet plunged into an icy state, possibly partially thawed, and then, again and again, slid back into a fresh round of cooling, until finally, somewhere near the end of this period, something happened that some researchers consider the most extreme phase of the entire crisis. An event known as the Huronian glaciation, recorded on the southern African continent and dated to roughly between 2, 3, and 2 billion years ago. Geological data from this specific episode, notably the low paleolatitude at which the corresponding glacial deposits were found, points to something extraordinary. The ice reached all the way to the planet's tropical latitudes. Stop and sit with that for a second, because it's genuinely hard to picture. Think about the equator, the hottest place on the planet, under any ordinary conditions, a region that, through every other climate swing in the rest of Earth's history, never once fully froze over. And now picture ice reaching that exact line, the one that was never supposed to be reachable by ice at all. Not the poles, not the mid-latitudes. the tropics. The planet froze over so completely that there was no warm refuge left anywhere for life to retreat to. This is direct evidence of what researchers call a snowball Earth state, a scenario where ice covers essentially the entire surface of the planet, pole to pole, including equatorial regions that never freeze under normal conditions. So, by the end of this act of our story, the planet found itself in a state it had most likely never experienced in its entire prior history. An almost solid ball of ice, locked inside a climate trap of its own making, triggered by the tiniest, most unremarkable residents of its own oceans. The next part of this story is about exactly what this ice-locked world looked like, and, most importantly, how any life at all managed to survive 300 million years of this icy imprisonment. The planet had frozen over, but this is exactly the moment to stop and picture what this world actually looked like, and, most importantly, how any life at all managed to survive being locked in ice for that long. Picture the planet's surface, seen from space at the time, solid, endless white, pole to pole, without a single break, without a single drop of open blue water anywhere. The oceans, the very same ones that gave rise to the first photosynthesis and to the oxygen catastrophe itself, now lay buried under a layer of ice that, by current climate model estimates, could have reached up to a kilometer thick. This is exactly the scenario scientists call Snowball Earth, not just expanded polar ice caps, the way ordinary ice ages work, but a complete, total freeze-over of the entire planet, including equatorial regions that never see snow under normal conditions. Formally, this glacial period, studied through the deposits around Lake Huron, spanned roughly 245 to 2 billion years ago, and by various researchers' estimates, the total duration of this icy episode, including all 3 waves of glaciation and everything in between, could have stretched to 300 million years, the longest glacial period in Earth's entire known history, longer than the time that's passed from the appearance of the first dinosaurs all the way to today. One of the most important and most counterintuitive aspects of the Snowball Earth state. Once the planet ends up in that condition, it becomes extraordinarily stable, almost stuck in that cold. And getting out of it requires far more extreme conditions than the ones that caused it to fall in the first place. Scientists describe this phenomenon as hysteresis, a system that, once it lands in a certain state, strongly resists going back, even after the original cause is gone. Stop and sit with that for a second, because it cuts against ordinary intuition. The natural assumption is, remove the cause, and things should eventually snap back to how they were. But that isn't how this works at all. Even if something had somehow yanked away every bit of excess ice all at once, the planet wouldn't have simply reset to its previous state. The system, once locked into this frozen condition, actively fought against reversing course, and getting out of the trap ended up requiring conditions far more extreme than whatever had caused the fall into it in the first place. Here's why. As long as the continents stayed buried under ice, the ordinary geological process that normally regulates atmospheric CO2, chemical weathering of rock under rainfall, which absorbs carbon dioxide, essentially shut down completely. No liquid rain, no liquid water on the continental surface, no weathering reaction. But the volcanoes didn't stop. The planet's tectonic activity, even despite that same magmatic lull we mentioned earlier, kept releasing carbon dioxide from deep underground into the atmosphere, just at a slower pace. And since nothing was left to absorb that gas anymore, it kept building up in the air, gradually, relentlessly, year after year, millennium after millennium. So what was happening, meanwhile, to life locked away under a kilometer of ice? Harsh as this world was, based on the available geological and geochemical evidence, life wasn't wiped out entirely. Researchers point to a few possible refuges where microorganisms could have survived this longest of all icy imprisonments. First, geothermal heat from deep within the planet. Even under a kilometer of ice, geological activity below never fully stopped, and in certain spots, especially where volcanic activity or hot springs warmed the ice from underneath, small pockets of liquid water could have formed right at the boundary between ice and ground, tiny oases of warmth in the middle of a global glacier. Second, The thick ice sheet itself may not have been entirely solid and impenetrable everywhere. Modern climate models, particularly ones that account for the effects of dust and cloud cover, suggest the possibility of patches of significantly thinner ice, and in some places even temporarily open water in equatorial regions. A scenario researchers sometimes name after the Norse mythological serpent Jörmungandr, said to encircle the entire world. Stop and picture that for a second. Somewhere along the equator of a planet buried under a mile of ice on either side, one thin ribbon of open or half-open water, wrapping all the way around the globe like something out of a myth. Except this one is a real, published scientific model, not a legend. In that narrow strip, photosynthetic life could have clung on, the last sliver of sunlight anywhere on the entire frozen planet. Third, the simple fact that cyanobacteria, the very organisms that caused this catastrophe in the first place, survived it and went on existing for billions of years afterward, leaving behind fossilized stromatolites and geochemical traces of continuous photosynthetic activity, even through the harshest stretches of glaciation, points to some kind of survival mechanism that let at least part of the biosphere hold on all the way through this ordeal. Life didn't thrive during these 300 million years. It survived, squeezed down to a bare minimum, scattered across the frozen planet in tiny, isolated pockets, waiting for the moment the icy trap would finally crack. And that moment, according to the traditional model, one that's been confirmed for decades now by geological studies of similar glaciation episodes later in the planet's history, arrived precisely because of the very mechanism we just described. The relentless buildup of volcanic carbon dioxide in an atmosphere stripped of its usual way of absorbing it. This buildup didn't take years. It took tens of millions of years. But once atmospheric CO2 concentration finally hit a critical threshold, by some model estimates roughly 100, possibly even 1,000 times higher than today's level, the greenhouse effect from all that accumulated carbon dioxide finally became powerful enough to crack the planet's icy shell. And when the melting finally began, it happened, according to researchers, not gradually, but almost explosively. A climate shift, stretched out over tens of thousands of years at its outer edge, threw the planet from the coldest state in its entire history, straight into one of the hottest, the exact opposite crisis, triggered by that very same surplus of accumulated greenhouse gas that had just helped melt the ice. 300 million years of ice didn't end in a quiet, gradual warming. It ended in a sharp, almost catastrophic swing to the opposite climate extreme. And what happened to the planet, to the ocean, and to the life that had survived inside it, over the following millions of years after this thaw, ended up permanently determining the future path of evolution on this planet. That's exactly where the final part of our story picks up. The ice retreated. The planet had just made it through the longest glacial period in its entire history, and broke free of it thanks to its own volcanoes. But the real question of this final act of our story is, what changed for good after this catastrophe? And why did it turn out to be not just a tragedy, but a turning point for all future life on the planet? Once the ice finally melted, and the carbon dioxide that had spent tens of millions of years building up gradually started getting absorbed again through restored chemical weathering of rock, the ocean that emerged from under the ice was significantly different from the one that had existed before the catastrophe. Geochemical studies find traces in rocks from this period of something scientists call the oxygen overshoot, or the Lomagundi event, a temporary, extraordinarily powerful spike in a positive carbon isotope anomaly, pointing to massive burial of organic carbon in sedimentary rock somewhere between roughly 22 and 2.06 billion years ago. Burying that much organic material, essentially, pushed the atmosphere even further toward accumulating free oxygen, since less organic matter was left available to decompose, which would otherwise have consumed that oxygen. But right on its heels came an anomaly of the opposite sign, just as extreme, a sharp, catastrophic collapse in the carbon isotope ratio, known as the Schunge-Franz-Villian event. Researchers link this collapse to the opposite process, a sudden, massive oxidation of previously buried organic carbon reserves as the first aerobic microorganisms, ones that had learned to use oxygen for respiration, started actively breaking down biomass accumulated over the preceding millions of years consuming a significant portion of the newly accumulated atmospheric oxygen in the process, which points to something unexpected. Oxygen levels in the atmosphere and ocean in the first several hundred million years after the Great Oxidation Event didn't rise smoothly and steadily. They swung back and forth like a pendulum, rising and falling again as the planet's biosphere, its geochemical cycles, and life itself all struggled to find a new point of balance in a world that had changed forever. And it was in this unstable, oscillating, but by now irreversibly oxygen-enriched world that something happened that finally justified all that chaos of the oxygen catastrophe and the glaciation that followed it. Researchers trace a direct chronological link: the expansion of so-called suboxic habitats, meaning partially oxygenated environments in shallow ocean waters between roughly 32 and 2. 1 billion years ago may have, in that exact window of time, created the first favorable conditions for something entirely new in the history of life. Complex, nucleated cells, or eukaryotes, the cell type from which every plant, every fungus, and every animal, including humans, would eventually descend. The most compelling, most dramatic evidence from this period comes from a site in southeastern Gabon, in Africa, known as the Francevillien Formation, dated to roughly 1 billion years ago. There, researchers found something that, at first, seemed impossible for a period this ancient: three-dimensional, structurally complex fossils, in some cases several centimeters across, far larger and more morphologically varied than anything previously found for this age. Stop and sit with that for a second, because it genuinely breaks the timeline you'd expect. For a long time, science assumed complex, mobile, multicellular organisms only showed up much later in Earth's history. And then, in Gabon, in Rock 2, 1 billion years old, someone found something that, at first glance, seemed physically impossible. Three-dimensional fossils, several centimeters across, with signs of active movement, capable of migrating in search of food. Not single-celled mud, not a bacterial film. Something behaving the way a far later, far more complex form of life should behave. Billions of years before, according to the old textbooks, that kind of complexity was even supposed to be possible. Detailed tomographic analysis of these structures revealed features researchers interpret as evidence of active mobility. An organism, most likely multicellular, capable of migrating, moving both horizontally and vertically in search of food resources, behavior modern scientists compare to the movement of amoeba-like cell colonies that band together into a migrating form when food runs short. Scientists named this find the Francevillien biota, and it remains the subject of intense scientific debate over exactly how advanced this form of life actually was. But the mere fact that it existed at all, combined with geochemical evidence of an oxygen-rich environment capable of supporting complex metabolism at exactly this period, paints a compelling picture. The crisis triggered by cyanobacteria, in the 300 million years of crisis that followed it, ultimately cleared the way for something far more complex than anything that had existed on the planet before. It's worth pausing here to spell out clearly why this ancient, almost forgotten catastrophe matters so fundamentally to everything that came after. Oxygen, the very same gas that triggered the first mass extinction in the history of life, and the very same gas that indirectly kicked off the planet's longest glacial period, turned out, at the same time, to be a necessary precondition for something without which none of the complex life we know today could exist at all. Aerobic respiration, the metabolic process that uses oxygen to extract energy from food, gives a cell many times more energy from the exact same amount of nutrients than any anaerobic process that existed before it. That energy surplus, according to current scientific understanding, became a critical precondition for the emergence of much larger, much more complex cells, ones capable of supporting internal organelles, a nucleus, and, eventually, multicellular organization. Without the Great Oxidation Event, without that desperate, almost catastrophic buildup of a gas toxic to most life at the time, the molecular foundation that would eventually allow fungi, plants, and animals to exist would never have come into being at all. And without the forced glaciation that followed, and without the refuges where the hardiest forms of microbial life managed to survive, The story of evolution on this planet could have gone in a completely different direction, or nowhere at all. So let's come back to the question this whole story started with. How did life nearly destroy itself with its own breath? And how did a planet locked in ice for 300 million years eventually thaw out? The answer turns out to be a story about an unexpected, almost paradoxical connection between catastrophe and opportunity. Cyanobacteria, the tiniest, most unremarkable residents of the ancient ocean, accidentally poisoned the planet's atmosphere with a gas that wiped out the vast majority of life at the time, and, in the process, set off a chain reaction that destroyed the climate balance that had kept the planet warm for billions of years. Earth, in response, froze for 300 million years, the longest glaciation in its entire history, held in that state by a self-reinforcing loop that could only be broken by the slow, tens of millions of years buildup of volcanic carbon dioxide. And when the ice finally retreated, it didn't leave behind an emptied, dead world. It left behind a planet ready for its next great step, the emergence of a new kind of cell, one able to use that same oxygen that had once nearly wiped out all life, as an energy source powerful enough to eventually build every complex form of life that has ever existed. The greatest ecological catastrophe in the history of Earth turned out to be, in the end, the single most important turning point on the road to you, the one listening to this story right now. Life didn't just survive its own biggest mistake. It turned that mistake into the foundation for everything that came after.